Is this molecule in cis or is it in trans? I look at this molecule and I know that it has, quote, cis-trans isomers because I can see that it's an alkene, and each of the carbons of the carbon-carbon double bond have two different groups hanging on them. The one carbon on the left has a chlorine and a hydrogen. Those are different. And the carbon on the right has a fluorine and a bromine on it. Those are different. So I know it has, quote, cis-trans isomers. But for me to figure out if it's cis or trans, I need to look and find two hydrogens hanging on, and I don't see the two hydrogens on there. I see four different groups actually hanging on there. And so that confuses me a little bit. I can draw the other version, so whether that one's cis or trans, I'm not sure just yet, but I can draw the other version by doing this, by flipping the bromine and fluorine around. I can draw the other version. So if the top one were, for instance, cis, the bottom one would be trans. But again, I don't know which one's cis and which one's trans. And because of this, a new nomenclature was developed to handle this problem. And that nomenclature, or that new system of nomenclature, is the Cahn-Ingold-Prelog system, which uses the E and Z system of nomenclature. E is from a German word meaning across, and the Z is a German word meaning together. And so when you see E and Z nomenclature in the name of a molecule, it really is just a cis-trans system, but it handles more complex alkene structures, just like we have there on the left. And so E across is really, in our heads, we can just think of that as being trans, and Z together, the Z meaning together, is really just cis. So if you feel comfortable with the cis-trans nomenclature, E and Z is pretty much just the same, except how we identify whether it's in cis or in trans, it takes a little bit more work. The EZ system uses a system of priorities. It prioritizes the groups hanging on those carbons. And so we have to establish a priority system for each of those groups. So the first rule is atoms with higher atomic number have higher priority. And so what you do is you take one of the carbons of the double bond, so I'll take the one on the right here on that top structure, and attached to that is a fluorine and a bromine. And we look at the fluorine and bromine. So we look at the atom directly attached to the carbon of the double bond, and we figure out what is the atomic number. So for that we need a periodic table. If you look on the periodic table, fluorine has a 9 atomic number and bromine has 35. And so bromine has the higher atomic number, therefore it has the higher priority. So the bromine is high priority and the fluorine is low priority when you compare those two groups hanging on that carbon atom. Now let's look at the other carbon atom. So for that one, we'll go ahead and put that in there, and now we're going to compare the chlorine to the hydrogen. We're looking at atomic numbers there. Hydrogen has an atomic number of 1. Chlorine has an atomic number of 17. 17 is greater than 1, and so chlorine has the higher atomic number. And so therefore, it would be considered to have the high priority, and hydrogen would be the low priority. So now we've identified and we prioritized each of the groups on each of the carbon atoms of that double bond. Because we have the high priority bromine and the high priority chlorine on opposite sides of the railroad track, we can see that that would be in what we would consider originally to be trans, but trans in the EZ system would be considered to be E. And so that's in the trans or the E conformation. If we look at the second structure down there that we have, you can see we already know that chlorine is the high on the one side and bromine is the high on the other side. So when we look at this, the high priority groups are both on the same side of the track, so that would be like in cis, or in the EZ system, that would be the Z structure, or the Z isomer of the two. So E and Z are isomers of each other, and they are essentially cis-trans isomers of each other. Now the rules get a little bit deeper than that, because typically we don't have a bunch of halogens hanging on these carbons of an alkene. We typically have a lot of carbons hanging on there, and so now you're thinking, wait a minute, if they're all carbons, they all have the same atomic number, and that's right. So there must be another rule, and so let's talk about that. So now let's look at this structure here. Again, we have another alkene. Each of the carbons have a different group attached to them. The left carbon has a methyl and a hydrogen. The right carbon has a methyl and an ethyl group. Those are all, each carbon is attached to two different groups. And so therefore this does have, quote, cis-trans isomers. But again, because I only see one hydrogen, not a second one, it's tough for me to determine whether this is a cis or a trans molecule. Now you might be looking at this thinking, oh look, there's two methyls, they're the same, so maybe it's cis. But again, that's not the way you do the rule. And so for this one, we have to use the EZ system of nomenclature, and let's walk through that process and how that works. So just like we did previously, we're going to take one of the carbons of the double bond, and we're going to look at to see what atom it is directly attached to. So we're looking at this bond and this bond. The carbon of the double bond, which I'll just call that carbon 1 for clarity's sake. Carbon 1, which is again part of that double bond. Let me go ahead and show the double bonds. Maybe that helps us a little bit. So again, this would be carbon 1 right there in the original structure. That carbon 1 is attached to a carbon and attached to a hydrogen. So we're just looking at those two atoms. These three H's I'm not looking at in this discussion just yet. We might get to it, but we probably don't need to on this one, but eventually we'll be looking at those things. But for now, we have a carbon and a hydrogen. We know that the atomic number of hydrogen, those are different, so we can look at atomic numbers. The atomic number of hydrogen is 1. The atomic number of carbon is 6. So 6 has the higher priority because it has the higher atomic number. And so I'll go ahead and put high on this side. And the hydrogen would be the low priority one. And we can do that because the carbon and hydrogen are different from each other. But now let's go to the other side. The other side, it gets a little bit different. So when we look at the other carbon, we're going to look at the two groups to see which one has higher priority. And if you look at the first atom that this carbon, which I'll call carbon 2, is attached to, it is each attached to a carbon atom. And so since each carbon atom is the atomic number of 6, one of them doesn't have a higher one than the other one, so I can't tell which one has higher priority yet. And so for that, we go on to what is that carbon bound to and take a look at the atomic numbers there. And so let's go one by one. The top carbon is attached to, and I'm going to put a different color to show this attachment, is attached to a hydrogen, and a hydrogen. And we can see that from those three hydrogens there, what's attached to it. So we're looking at what's in blue there around that carbon. What's attached to the carbon on the lower group? What's attached to this carbon here? If you look at that carbon, it's attached to a hydrogen, another hydrogen, and a carbon. That carbon, this carbon here, being that carbon there. And so when we look at that, notice there's 3 hydrogens, each has the atomic number of 1, and then on the lower one you have 2 hydrogens and a carbon. That would get higher priority because essentially if you want to do it by just adding them all up, you'll see that you'll have 8 atomic units, atomic numbers associated if you add them all up at the bottom one, and 3 hydrogen is 1, hydrogen is 1, hydrogen is 1. That's 3 on the top one. And so in this case, the lower group has the high priority, and the one on the top, that methyl group, has the low priority. So what this means is, to determine priorities, you just keep moving down the carbon chain until you finally see a difference between what's attached to that carbon. And so in this case now, based on all that, we can drive the railroad text on through the carbon-carbon double bond, and you see a high group on one side of the tracks, the other high group is on the other side of the tracks. So that feels like a trans situation. Again, we wouldn't call this trans. Technically, we would call it the E conformation, is what we would see there. I'll just name this really quick, incorporating the E into the name, just so you can see how that goes in there. I've numbered the carbons of the carbon chain. We can see that there's 5 of them, so that makes this a pent. It has a carbon-carbon double bond, so I know it's a pentene, and the double bonds on the second carbon, so it's a 2-pentene. And then we got this methyl group hanging on carbon 3, so that makes it 3-methyl 2-pentene. And if it was a trans molecule, we could just put trans right out in front of it, because this technically isn't trans because it doesn't have the 2 hydrogens. We use the EZ system of nomenclature, so really what we should put in here is, sorry I'm jamming it all in here, but it would be E. Oh, it's not letting me put that little E in there, right? Try this again. E dash, sorry that dash is really far away, and for some reason my methyl went away. So it'd be E-3-methyl-2-pentene would be the appropriate name of this molecule that we drew here. The last thing I need to just mention really quickly is, what if there's a carbon-carbon double bond in one of those groups? So take a look at this structure here. So again, we're trying to determine whether this carbon-carbon double bond is in E or Z conformation, or the E or Z isomer, so specifically for that double bond. And so to do that, we'd be comparing the two groups and assigning priorities. And so I started that below, and you can see here, after the first atom that's attached, we can see they're both carbons. We need to go on to the next one. And so for that, I'll change the color just so we can see exactly what bonds we're looking at. And so the lower one, the methyl group there, would have 3 hydrogens attached to it. And so we draw it like that, so it has 3 H's. The top carbon has a hydrogen attached to it, and then notice it has a double bond to carbon. The way we do this, though, for determining priorities, is we count those 2 bonds separately, and so we would count them like that. And so it would be a carbon, and a hydrogen would be what's attached to it. So any double bond, you just count that atom twice in the proper priority naming rule. So obviously the top group would get higher priority because it has 2 carbons and 1 hydrogen, which has more atomic number total than the bottom methyl group, which only has 3 hydrogens. Hope this video helps you understand the EZ system. If you understand the cis-trans system, I hope you can see that really the EZ system is pretty similar to it. The idea is the same. The nomenclature just changes a little bit. I'm going to post a practice problem slides or practice problem video that you can practice the EZ system of naming. It'll have explanations, so I'll walk through all that, so be looking for that. Take a look at that. That may help solidify your understanding of the EZ system.